All right, good morning, everyone. Can you guys see my screen and hear me okay?
Yeah.
Okay, thanks. All right, hope you guys had a nice weekend. Today, we're going to be doing our final lesson, finishing up 7.2, dealing with volume with known cross sections. Now, this is just going to feel like we're adapting our disk method and washer method a little bit. So a lot of things that we did with disk and washer method is still going to apply. The way that we find bounds is going to apply. The way that we find radius is going to apply. We're not going to call it radius anymore, but we're still doing a top minus bottom or right minus left. We're still having to make our adjustments with our expressions if we're doing right minus left. So you're going to see a lot of carryover with this method and washer method. It's just that instead of a circular based object, now our objects are going to have different shapes involved. It may not be a circle anymore. It could be rectangular based, triangle based, semicircle based. Okay. The shapes will look a lot different, but our procedure will feel very much, we're just making some slight adjustments with our procedure. Okay, but I want to kind of start from with this method and washer method, just so that we can kind of review and also see where that distinction is going to come into play when we talk about cross section. So with this method, we know that we always start off with some shaded region, right? So let's say we have some shaded region here. We're rotating that region around the x-axis. And with that rotation, we know that there's going to be a circle involvement, right? Anytime we're rotating anything 360 degrees, there's always going to be a circular element to our object. And also, just by looking at where our shaded region is in relation to our axis of revolution, we see there's no gap. Our axis is up against a flat surface, so we know that we're dealing with this method, which means that we only need one radius. Okay, and we always drew our radius perpendicular to our axis because that was how we came across our radius. And from there, we found that distance, either top minus bottom or right minus left, and then we insert it into our disk method formula. Okay. Now I want you to see something here. Well, from x1 to x2. You see how we started with a representative radius and representative circle, but then we accumulated that circle from one end, or that disk from one end to the other. But this is the area of a circle, right? Pi r squared. So what we're doing different today is we are no longer going to be rotating, which means that there may not be circles involved. We're going to be building different shaped objects on top of a base. So that means this is going to change. We're still going to have the integral. We're still going to have our bounds, but now our shape is going to change. It's not necessarily going to be circles anymore. It could be squares, it could be right triangles, it could be equilateral triangle, it could be a rectangle, it could be a semicircle. So whatever the problem calls for, we're just going to be replacing this piece with the appropriate area formula. Okay. With washer method, same idea, right? Washer method, we had a shaded region to begin with, but the difference is that there's now a significant gap, either up against the curved surface or not even touching at all. But either way, we knew that there was a gap. We're still rotating, but we have to make an adjustment with the fact that we got to subtract out a hole that we don't want to include as part of our volume. So we have to find two radius, a big radius and a small radius, and take time to essentially subtract the smaller circle from the larger circle. So we can see that built into our volume formula as well. Big R squared minus little r squared. But you can see built into this formula is also area of circle. It's just that we're taking the additional step of subtracting the smaller circle. So the resulting area is actually circular rings, but they're kind of all based off of the same idea, right? Rotation is going to result in circles. So the volume problems that we've been working on, this and Washer, have all involved taking a shaded region and rotating it. And that rotation is causing these circle shapes to come out, or circle related shapes to come out. So we have area is pi r squared, or pi r squared minus little or pi little r squared. Okay. So the reason, let's see. So cross section is the shape that results if we were to cut the object in half and look at the resulting shape on the inside. So if I were to slice this disc either here or in the middle or in the back, if I open it up, I'm going to see circular rings, right? So I'm going to always get a consistent cross-section shape no matter where I slice it, as long as I'm slicing in this orientation. Same thing here, right? I could be opening this, I could be slicing this object here, or here, or here, anywhere. If I open it up, I'm going to see circles, right? And so these are problems that have circular cross sections. Okay. All right, but now we're dealing with objects that are not necessarily going to be circular cross sections. Okay, so the way we're going to do that is we're going to be starting with some shaded region. Okay, let's say this is first quadrant here, this little quarter circle here. But that's just the base. The shape of the base has no bearing on what we're dealing with. Okay, so don't look at the shape of the base. It's just we're just building different things on top of this base. But instead of rotating this shaded region, we're going to be building things on top of this base. So this is kind of drawn in a kind of three-dimensional perspective. We're going to be building cross-section area on top of this base, no longer rotation. So for this example that you see in front of you, this is building squares on top of this base. So we're starting here. So you see how that is a relatively short length. So so imagine a square coming out of that page that also has the same distance. You can imagine that's going to be a pretty small square here. But a square that is here is going to be a little bit longer in height. It's going to be taller in height, right? Because if my base is this height, is this distance, then it's got to be extending that distance coming out of the page. And the largest square is going to be here because this has the longest distance space, and we know that the height must also be the same value, because if we're talking about a square, the base and width has to be the same. So you can kind of see how this is kind of built, right? All these differently shaped squares based off of the distance from the curve to the respective x value or value on the x-axis. We're going to get increasingly larger squares, and it's just going to stack until we get some kind of oddly shaped object. Okay. But even though this is an object that we don't recognize, it's not like an everyday object that we recognize in everyday life. We don't have to draw it. We just have to understand that whatever object we create, there's this consistency where no matter where I open this up, I could open it up here or here or here. If I open it up, I'm going to get differently sized squares, right? But they're all going to be squares, right? As long as I'm slicing it in this orientation. Okay. Okay, so we're just going to be building different shapes on top of a base again, we don't have to worry about what it looks like. We just have to be able to understand that understand how to find the volume of whatever is described in the problem. Okay, so let's look at example 1 here. Find the volume of a solid if the base is bounded by the curve square root of 1 minus x squared, y equals 0, x equals 0 in the first quadrant. Cross sections are squares parallel to the y-axis. So this example 1 is, we're just building this right here. We're building, we're trying to find the volume of this specific object. Okay, but I'm going to be drawing it in more of a two-dimensional perspective here. So here's my x and y axis. Y equals square root of 1 minus x squared. That's just going to be a quarter circle in the first quadrant here. There's my shaded region. Okay, so now that we have our shaded region, we have to be able to figure out which orientation do we want our length to be. Do we want it to be vertical or horizontal? But when we do cross sections, we're still going to be doing top minus bottom or right minus left, but then we just have a different perspective. It's going to represent something else. So if it was area, then we would just do, we would call this a rectangle, right? Adding infinite numbers of rectangles from one end to the other. If we're rotating it, then we call that distance the radius because we're rotating that value and it's going to go into the area of a circle. But now I'm going to call it base, and that base is going to be representative of whatever length is going to be sitting on that base. It could be the length of a square. It could be the leg of a triangle. It could be the hypotenuse of a triangle. It could be the diameter of a semicircle. But whatever it is, I'm just going to call it base and then plug it into whatever area we want to use it for. So we're always going to be given very specific instructions as to how to draw that base length. Is that base going to be vertical or is it going to be horizontal? And we always want to start there. After we have our shaded region, this is our next step. Which direction do we want to put our base length? So parallel to the y-axis. So y-axis is vertical. I'm sorry, yeah, vertical. We want something parallel to it, so we want something in the same direction as vertical, so we're going to keep it vertical. Okay. So my base length is going to be vertical. Before I called it rectangles, or I would call it radius, but now for the perspective of cross sections, we're going to call that the base length. But we're going to treat this the same way that we would with radius. The next step is the same, right? We see a vertical base, just like how we would treat a vertical radius, we would do top minus bottom. If we do top minus bottom, we know that every equation that's given to us is pretty much already set to go. There's no need to make adjustments like we would if it was a right minus left. So let's identify the top and the bottom. The top is sitting on the curve, which is square root of 1 minus x squared. The bottom is sitting on the 0. So we just do top minus bottom. Top of the base is sitting on the curve, minus parentheses, and the bottom is sitting on the 0. Y equals 0. Okay, we know there's minus 0 will just go away, so base is equal to square root of 1 minus x squared. And now we have to figure out what area that we're going to be using this for. So the area that we're going to be using this for is squares. So we go and we search for area of a square. So no longer is this going to be radius pi r squared, right? Now we have a different formula. that we're asking to do. We're using squares here. So area is just going to be base squared because we want squares to be built on top of this region. Okay, so all I'm going to do is I'm going to take my specific base value and insert it into my formula. All right, now I have my area, and now I'm just going to insert it into my integral, right? Because this will give me one representative area, but I want to accumulate all these squares from one end to the other, and that's where the integral notation is going to come in. So my volume formula is going to be integral from x1 to x2, because we're doing top minus bottom, and I'm just going to insert my new area formula that I want to use. So I'm not going to put pi r squared here because I'm not doing circles. I'm going to be putting something that is the shape that we're asked to do, which is squares. So this is going to go in this area portion here. Okay. We still need to find the bounds. So the bounds we're going to extend from, we're building squares from one end to the other. So all these different size squares, we have to start at 0 because that's the furthest left. And we got to end at that intersecting point. So that intersecting point, we're going to find that by setting the two equations equal. So intersection is just square root of 1 minus x squared is equal to 0. Intersection of the curve with the x-axis. I square both sides. I get 1 minus x squared is equal to 0. Solve for x. X squared equals 1. Take the square root. I get x equals plus or minus 1. Now, the negative 1 is not going to make an impact because that's outside of our shaded region. So we're only going to go from 0 to 1. Okay, so there is my adapted formula here. Volume equals integral from 0 to 1. Base, there's my area, right? Replace my area with everything I see here. Okay. You're more than welcome to enter this in the calculator. I just see that this is something that I can reduce so that I don't have to put as much messiness into the calculator. I see the square root and the square are perfectly mashed up where I can just cancel them out. So volume equals the integral from 0 to 1 of 1 minus x squared dx. Okay, so now I'm ready to put this into the calculator. You can do this by hand, but it's probably easier to just put in the calculator here. So 1 minus x squared . 0.6, see if it'll get down to a fractional value. It does, 2/3. So volume is just 2/3 units cubed. Now you may be tempted to just put pi there because we've done pi so many times with our volume, but notice again, this shape does not have any circle. There's no rotation going on. It's not circle based. So no pi for most cross sections, except for semicircles. That's the only time that we're going to have something that is circle related, and pi is going to creep back into the formula, but everything else, no pi for your answer. Okay, any questions with the process or procedure? Okay, so hopefully you guys find this to be very similar in how we approach disk and washer method, right? We're still finding some distance, but instead of calling it radius, we're calling it base. And instead of inserting radius into pi r squared to get circle area, we're plugging base into an area formula adapted to whatever shape we want to use. And then rather than doing integral of pi r squared, now we're doing area of another shape, another area formula. Our bounds are, we still look for bounds the same way if this was disk method or washer method. We just have to make a slight adjustment into this region here. Instead of pi r squared, we're putting something else here based off of one of these 6 formulas. Okay. All right, let's go to the back page. All right, example 2. Find the volume of the solid if the base is bounded by the curve y equals x squared and the line y equals 4. And the cross sections are isosceles right triangles whose hypotenuse lie on the base and are parallel to the x-axis. All right, so first things first, I need to know where the shaded region is. So y equals x squared and y equals 4. That's just a parabola with a vertex at 0, 0, and the horizontal line at y equals 4. There's my parabola. Here's my horizontal line. And then here's my shaded region. So our next step is deciding how do we want to draw our base length, right? Do we want it to be horizontal or do we want it to be vertical? And we have specific instructions as to how to draw it. Parallel to the x-axis. So x-axis is this way. Parallel to the x-axis, so we want it in the same direction, so still horizontal. So we have a horizontal base, which we would approach the same way if we had a horizontal radius or a horizontal rectangle. Horizontal radius for this method or washer method, we know we have to do some adjustments. Our equations are not going to be in the right form. So that means it would be perfect for top minus bottom as y equals, but not quite for right minus left. So we're going to have to work with our curve here. So our curve was or is y equals x squared, but it's not in the right form. We have to solve for x. So I'm going to get x by itself by taking the square root. A plus or minus is going to pop up. So I get plus or minus square root of y is equal to x. Now, these are 2 separate branches here. We have x equals square root of y, which will show a positive x value, and that's going to be here. All right, it's referring to this branch here. Now x equals negative square root of y. That's going to guarantee a negative value. And negative value is going to be this side here, negative x values. So x is equal to negative square root of y. That's referring to this right here. So that's perfect, right? Because we have we're doing right minus left, and we have identified what the right and the left endpoint of my base is sitting on. And we're going to be able to find that representative distance of that base length. Okay, so we do right minus left. Right endpoint is sitting on the root y minus big parentheses. Left endpoint of my radius, of my base is sitting on the negative root y. And all my equations are in perfect form for that, right? X equals, that's exactly what I need if I want to do anything with right minus left. Do a little bit of cleanup here. Our base is just going to be root y plus root y. So it's 2 root y. And we can insert that into our area formula. Let's see, what area do we want to have this base to be part of? It's telling us isosceles right triangle whose hypotenuse lie on the base. So we'll go searching for that formula there. Right here, right? Isosceles right triangle with hypotenuse on the base. This formula is already adapted for that scenario. So 1/4 base squared. Okay, we have the formula identified. Now we're going to be updating the formula with a specific base that we found, which is 2 root y. Okay, any questions so far? Okay, maybe I'll do a little bit of cleanup in a bit, but I know that this is going to get inserted into my volume formula because I want to accumulate all these triangles from one end to the other. So let me just put my volume formula here. I'm just inserting whatever area that I want to put. In this case, I want area of isosceles right triangle. So this is going to go in this slot here. Okay, we have to adjust our bounds as well, right? We're not stacking these triangles from this end to this end. We're stacking these triangles that are coming out of the page from this side to this side. And you know, it's hard to draw what this picture is going to look like, but you kind of imagine if this is the hypotenuse, you're going to see a triangle kind of stick out of the page. And the right triangle is going to be up at the top here. So imagine all these triangles that are coming out of the page. They're all kind of vertically stacked from one end to the other end. And we can tell where those bounds are, right? We don't have to use any algebraic expressions to find that intersection. We can just tell, okay, the lowest y value that I see is 0. The highest y value of my shaded region is 4, so those are my bounds. Those are my y1 to y2 bounds. And I'm looking at that 1/4 2 root y squared. I can enter this in here, but I'm just thinking, what if I can just do a little bit of cleanup, and that way I don't have to do as much keystrokes or messiness into my calculator. So I'm looking at that 1/4 2 times root y. I'm thinking about just cleaning this up. So I can square the 2, which is 4. I can square the square root, which is just going to turn this into y. So I get 4 times y. Okay, I'm just squaring the 2 and squaring the square root. And the 1/4 and 4 will just clean up nicely. I can just take those out. And I'm just left with y. So my area, all this just cleans up to be y. You can enter in the calculator, but I'm just going to work this out by hand. This is easy enough for me to do by hand. So power rule, y becomes y squared over 2. evaluate my upper and lower bound. Upper bound gets plugged in first, so 4 squared is 16 over 2, minus 0 squared over 2. I get 16 over 2 is 8. 8 minus 0 is just 8. So my volume is just 8 units cubed. Again, there's no circle within any of my shaded region here. So no pi involved, just 8. Okay, questions so far? Okay, example 3. Find the volume of the solid if the base is bounded by the curve y equals x squared and the line y equals 4. Cross sections are semicircles whose base are perpendicular to the y-axis. Now, if you look, it's the same shaded region. So I'm just going to redraw this here. Here's y equals x squared. Here's y equals 4. And then here's my shaded region. All right. Next step, we have to decide how we want to draw this base length. Do we want it to be vertical? Do we want it to be horizontal? And again, we're always going to be given very specific instructions of how to draw it. So let's look. Perpendicular to the y-axis. Okay, so let's think about that. Y-axis is vertical, but I want something perpendicular to it. So it's going to have to be back to horizontal, right? Perpendicular to the y-axis. So if you look, it's the same orientation as example 2, but the wording is a little bit different. So I want to point this out, that there are different ways that the problem can say horizontal or vertical. But we have to get used to this language here because this is the way that for some reason AP exams for cross sections are going to ask or are going to present the problem in this way. Asked you to be careful because just because you see perpendicular or parallel, it doesn't mean that it's always going to be one direction or the other. You want to decide what is it in relation to? Is it in relation to the x-axis or the y-axis? Because just because you have parallel or perpendicular doesn't always guarantee a horizontal or vertical. So take the time, to convince yourself using the full description whether you want to draw a horizontal base or a vertical base. Okay. All right, so the nice thing though is that a lot of things we did for example 2 will just carry over, right? Our base is still going to be right minus left. We're going to be able to use the same base. We're going to use the same bounds. The only thing different is that our area is going to be different, right? We're putting into a different area formula, but it's still going to be same base and same bounds. So it's going to speed things up here. We know this is going to be x equals root y. Just like before, this is x equals negative root y. Okay, right minus left, minus parentheses. We know it's going to be 2 root y. The area is no longer going to be triangles. Now they're going to be semicircles. So pi is going to kind of creep into our formula again here. We have a very specific base. Go into our formula there. I'm going to try to clean this up whenever I see pi, I want to just leave it out because I don't want to insert it into the calculator just so I can improve my approximation or improve my volume, or eventually will be my volume. So I'm going to do a little bit of cleanup here. Pi over 8. I'm going to square both these terms in size. So 2 squared is 4. Square root of y squared is just going to be y. So 4y. All right, same process that I did above here. But I see that 4 over 8 can be reduced to 1/2, and I'm just going to push the pi out in front. So pi times 1/2 y. All right, so that's my area cleaned up. And I'm just going to insert into my volume formula, which is going to be very similar, right? Right minus left. But I'm just going to put a pi in front and the 1/2 y inside the integral. I'm going to be stacking these semicircles from one end to the other. So imagine these semicircles are just sticking out of the page, and we're stacking it from one end to the other, so from 0 all the way to 4. All right, same base as before, same bounds, just different area. Okay, so I'm going to enter this in the calculator, leave pi out of it. .5x. I get 4, that's my volume. I'm going to attach pi just like how I did with disk and washer method.
Mr. Yang,
Yes.
I plugged pi into the calculator with it and got the same answer. Is there a reason we don't plug pi in the equation?
So you plug pi and it came out as pi?
Yeah, I did pi over 8 times 4y. I didn't reduce it to pi times 1/2.
That's fine. And you were still able to get, the calculator still gave you in terms of pi?
Mm-hmm.
That's great. Yeah. I think I don't know if the 84 is going to do that. Maybe the 36 Pro does it. Maybe it still gives you something in terms of pi. So that's great. It's just that if I do it in here, it's going to give me a decimal number, and I prefer an exact value. But if your calculator does it, then perfect.
Okay, thank you.
Okay. All right. Any questions so far? Are we okay? So I really want you guys to be able to look at this and just feel like, okay, I'm just making a slight adjustment with disk and washer method. I'm not starting from scratch, right? A lot of, everything that we've already kind of gone through, we're using, right? We're using the same way that we find radius, the same way that we find base, the same way that we find the bounds, the same way that we find the bounds here. We're just making a slight adjustment into this area section because we're no longer dealing with circles. So we're just inserting this with the appropriate formula that's been established. All right, one last one here. Example 4. We have our shaded region, natural log of x, and 1/2 x minus 1. The natural log of x is the curve, and the 1/2 x minus 1 is the linear graph. All right, first order of business. Well, I'm going to identify them first. All right, first thing we have to establish is what direction do we want to draw our base? Do we want it to be a vertical, top minus bottom, or do we want to do horizontal, right minus left? Okay. All right, let's see what they say. Perpendicular to the x-axis. That's the instruction. So x-axis is here. We want something perpendicular to it. So we got to switch it to a vertical. So we have a vertical base. which is probably the base that we prefer because everything is going to already be in place for a vertical. Top minus bottom, our equations are set to go. They're all in the form of y equals. So we know that top minus bottom is typically less work in terms of setup and putting into the formula. So there's already set up for it. We're going to go jump directly into our base expression. Okay, so top minus bottom, the top of my base, my representative base is sitting on the curve, which is natural log of x, minus the bottom. So the bottom is sitting on the 1/2 x minus 1. And now I'm just going to distribute the negative through and write my expression here. Okay. Now that I have my base length, I have to decide what area do I want to insert this base into. And the area that I'm working with is isosceles right triangle with a leg in the region. So let's go searching for that formula there. Isosceles right triangle with a leg on the base. That's going to be 1/2 base squared. So I'm going to take my specific base value and insert it into the base of my formula that I've identified. So there's our area. Now we're ready to insert it into our volume formula for top minus bottom. So integral from x1 to x2, I'm just going to insert what I found for area into this space here. So that's the last thing we need to look for, right? We don't have the bounds yet, but I'm just going to put everything else in place, and we can worry about that. So I'm missing my bounds. I know my bounds must be in terms of x. So I know it's going to be this x value and this x value. And we can tell that those x values are simply the intersection of natural log and 1/2 x minus 1. But it's going to be tough to work this out by hand. So we're going to use our calculators. We're going to find the intersections using our calculators. I'll show using the graphing first, and then I'll show using the 36 Pro. All right, so we're looking for intersections here. But first, I'm just going to graph those two curves. Go to y equals. Under y1, I'm going to use natural log of x. Under y2, I'll identify the g of x, the bottom function, the 0.5x minus 1. And I'm just going to go to zoom 6. If I go to zoom 6, it'll just give me that standard window. And then from that standard window, I can decide, oh, am I seeing enough? Do I need to zoom in or zoom out? And I can make a decision after I have some standard window to work from. Okay, hit enter. All right, so we see that shape taking place. We see that our what I have in the calculator is not as clear as I would like for it to be because I'm a little bit zoomed out. So I'm going to zoom in a little bit. I'm going to go to zoom box. So if I do zoom box, I'm just going to be able to create a box around that region that I want to look at. So I have a blinking cursor. I'm going to move that cursor to where I think is the upper corner of where I want my box to be. So I'm just going to create a box right in this region here. So maybe I'll go a little bit higher. Hit enter once, and then you're going to be able to start getting to the width of the box, a little past the intersection if possible, and then don't hit enter, but just use the down arrow button. Okay, enter. Now it's going to just look at the what's inside that box. So we can see things a little bit more clearly. It resembles our graph a little better. And now I'm going to be able to identify the two graphs and find the intersection. So I'm going to look for the left intersection first. So go to second trace and then select intersect. So go to second trace, it'll take you to calculate, go to intersect, and now the calculator knows that we want to look for an intersection of two graphs. But we're going to have to tell the calculator which graphs to look at. It may seem obvious, there's only two graphs here, but we still have to tell the calculator. So it's asking, all right, what do you want to identify as your first curve? So I'm on the natural log of x graph. I'll just move it closer to where I think that natural log of x is, or that intersection is. Hit enter. And now calculator is saying, where do you want my second curve to be? And I want it to be on this line here. I want it to be relatively close to my intersection again. Hit enter. And now guess, we want the calculator to guess that approximation. So hit enter. And it's going to find that intersection for us. Okay, 0.464 is what we're after. We're after the x value. The y value would be good if it was a right minus left, and we're trying to build triangles from the bottom to the top, but we're looking for x values, right? Our bounds are in terms of x. So we only need this x value here, 0.464. Okay, so that's my left bound here. I'm also going to look for my right bound. So go to second trace, intersect again. But now I'm going to scroll over to a point on the natural log graph that's closer to my other intersection that I want to target. So go close to it, but not directly on it. Hit enter. My blinking cursor is now on the other graph, which is the line. I'm going to hit enter again, just relatively close so that it knows to look for this intersection. Hit enter. Guess question mark, hit enter again. And now it's going to target that x value for us. So 5.357. Okay, so then I'm ready to plug in the calculator, right? Everything I see here, I can just go into my integral, Math 9 feature, or your integral notation in your 36 Pro. I do want to show how to find the intersection or go through the steps of finding the intersection using your 36 Pro. So there's no graphing feature here, but we do have numsolve. So if you go to second sign, I'll take you to numsolve. And then you're going to put the two functions on either side of the equal sign. So I started with the natural log of x. Doesn't really matter which side is which. I just started with natural log of x on the left side. And I put 0.5x minus 1 on the other. And I'm just going to look for the intersection of these two. Now, there's two intersections, so we're going to have to tell the calculator which point to search, or at least what, give it a value so that it can search for the closest intersection from that x value. So hit enter. Now you can tell that this intersection is between 0 and 1, right? So you can either put 0 or 1 down and it'll find that intersection for us. So you can do 0 or 1. It'll both give you the same value. Hit enter. And it should find this intersection for us. It does, 0.464. That's our left bound. Okay, solve again. Yes, we want to find that other intersection, so hit enter. But now I got to tell it what number to look at, because we already searched this one. We want to now give it another value to start from. So either 5 or 6, because we know that intersection is between 5 and 6. Let's just say 6. Okay, it doesn't really matter. I'm going to start at 6 look for that closest intersection, make the calculator find it for us. It should give us that value somewhere between 5 and 6. And here we have it, 5.36. Sorry, 5.357. Right? And then we just enter all this in the calculator. Math 9. I think I already have it saved here. So I already entered it previously. So I'll just walk through what I entered in. Okay, so bounds from 0.464 to 5.357. Next thing I did was I entered in 0.5 to represent the 1/2. I did a big parentheses, natural log of x minus 1/2 x or 0.5x plus 1, close parentheses, and then I squared as well. So I want to make sure I square my resulting expression all inside the parentheses. Make sure you put a dx, 0.613. Again, no circles involved, no rotation involved, so there's no pi. So just 0.613 is all we need to find our volume. Let's see, it doesn't convert to a fraction, so decimal is perfectly fine. Okay, any questions? Okay, so we're able to get through what I want to get through today with cross sections. I may have a help session this afternoon. If I do, I'll send out a remind and I'll open up that help session page at 3:30. And if there's other help sessions, I will also be sure to both record it and to send you a remind about any upcoming ones. But we have tomorrow and Wednesday to do test review. This is the only topic that we're dealing with area and these 3 sub volume sections with this method, washer method, and cross section. And we're just going to be practicing with that over these next 2 days. So understanding the orientation, that's if we need to do orientation for right minus left, we have to make sure we practice getting our expressions in the right format, our bounds are that we're looking for the right bounds, practicing with our calculator to find approximations if we need to, and also using the calculator to find the integral. So, but yeah, that's going to be our goal for the next 2 days to get ready for our test on Thursday. Okay. Any questions you guys have? All right. Thanks, everyone. Hope you guys have a great day. I'll see you guys tomorrow and let you know if I have a help session this afternoon. All right. Take care, guys.